Good afternoon, everybody. Welcome to this afternoon's C3.ai Digital Transformation Institute colloquium. Just to those of you who might be joining the seminar for the first time, the goal of the C3.ai Digital Transformation Institute is to really create this science and technology of digital transformation, which is really transforming all aspects of our government, society, and most importantly, business and industry. It's funded by C3.ai and Microsoft, a few industrial partners as well. It's co-led by University of Illinois and Berkeley, and we're pleased to have as our lead university partners Carnegie Mellon's KTH, the Royal Institute of Technology in Stockholm, MIT, LBL, the National Center for Supercomputing and its Applications, Princeton, Stanford, and the University of Chicago. And, for the end of the term, we have 2 more talks, but the seminar series is not going to stop. We're going to keep going in June, July, and it'll be through the summer. Next week is Jeff Sharma from the University of Illinois talking about game theory and learning, and feedback. It's called feedback control perspectives on, as you know, there's a big set of discussions that Jeff has been involved in between reinforcement learning and control, model predictive control. And then Louis Shaw, also from the University of Illinois, will talk about what he's been doing for best practice guidance with the local medical provider, Carly, in Urbana-Champaign on best practices. Everything we do is available on our YouTube channel, which is listed. This presentation, of course, is about 45 minutes long, and please hold your questions to, well, you can certainly put them up anytime you want, but the speaker will answer them. Camille will help moderate the question and answer with me at the end of his talk. And you can upvote questions, etc., etc. Okay, so today you have a great treat. It's first of all, you have a fantastic speaker and a great friend. So I can assure you, he's also will be most thought-provoking. Every time Stefano has given a talk at Berkeley, there have been numerous PhD dissertations that have been hatched by his talks. So anyhow, I think this may also be true in the audience that there is. So this one is called Graceful AI, Backward Compatibility, Positive Congruent Training, and the Search for Desirability Behavior of Deep Neural Networks. So all topics which are certainly close to our hearts. And so let me introduce you. I've known Stefano quite a while, I think, from the time he was an undergraduate at the University of Padua and then a graduate student at Caltech, and then Washington University, St. Louis, Harvard, and then back to UCLA. And, he's a professor of computer science at UCLA and the founder of the Vision Lab. But most recently, he has been the VP of Applied Science at the Amazon Web Services, at Amazon's Web Services AI, and he runs a lab which I think is on the Caltech campus. But the things that he oversees research on are fantastic, and they're not just in Pasadena. They include vision, speech, and these are the specific programs there. Custom labels look out for vision, natural language, Amazon Comprehend, Amazon Lex, Amazon Kendra, Amazon Translate. All of these are really, thanks to the incredible success of Amazon, all staples of the products that you use. And in fact, if there was one company that really personifies digital transformation and personifies the power of digital transformation, I would say it's Amazon. So without further ado, let me turn over the floor, and I will stop sharing. Stefano, I will also welcome and thank you so much for doing this. and I'm going to go off the air also.
Thank you, Shankar. It's a very, very kind introduction. Indeed, it's a great pleasure to be here. Can you all see my screen?
Yes.
Okay, great. So as Shankar says, one of the luxuries of being at AWS is that you get exposed to a number of new problems. And one of the pleasures of being an academic at AWS is that some of the problems you would not think of when sitting in your office, in your lab. So today I will give you some examples of some of the projects that we are undertaking at AWS that collectively go under the name of Graceful AI. And I'll show that with a couple of examples. I will start with an anecdote. Now, at Amazon, we do customer-obsessed science. And so this is a stylized conversation between a customer and a scientist. It's actually a conversation that happened in 2018. And so we were discussing a service that the customer was complaining is not accurate enough. And the scientist was puzzled because this service happened to be uniformly the top performing on all the data sets and benchmarks that have been tried, both public and internal. And so he wanted to go and look at what is not working, and the customer says, well, when you use a deep learning model, usually it's not in isolation, but it's in the context of some workflow and there is post-processing. In this case, the customer was using a model to cluster some entities. And when the scientists look at this, says, wait a second, you're using a version from years ago. We have updated model multiple times since then. Why didn't you update? And the customer says, well, because of backfilling, of course. What is backfilling? And so, the new model is twice as fast, half the error. What's wrong? What's not to love? And so, well, this is a huge cost, both in terms of time, effort, and money, of course. So what is backfilling? This is something that you might have experienced when you update the software that manages your photo collection. Usually after the update, your photos are not available for a period of time, which could be in the order of hours or days or weeks or months if you have billions of images. And during this time, what's happening is the following. So typically, let's say this is your photo collection on your computer. Your images are passed through some deep learning model that generates some type of representation, call it embedding, call it features. And these are vectors in some high-dimensional vector space. And then in this space, when you get a query picture that you want to match, let's say, to your cousin, that gets processed to generate its own embedding or representation, and then those get compared, for instance, using nearest neighbor or anything else from that. So what happens when you introduce a new model is that the query image gets processed to the new model and generates a representation in a space that is different from the one where your gallery sits. So these are vector spaces that could have different dimension. They could be computed with a different architecture, optimizing a different loss function. So they're just not comparable. And so backfilling consists of reprocessing the entire gallery, every single image that's on your computer, so that you can generate a new gallery and therefore compare to any query image that comes along. Okay, so this is what's called backfilling, sometimes called reindexing. And now you can imagine that if you are a company that has billions of images, this is quite an onerous process, to the point that many companies prefer to forego the benefits of the update so that they don't have to go through this complex reindexing. Okay, so and in fact, all the improvements that we as scientists produce, and every conference we go to, we have improvements after improvements. These end up often sitting on the shelves just because improvement alone is not sufficient. And so at that time, back 2018, we said, well, why should anybody have to reprocess all data? Why don't we train the new model in a way which is compatible with the old gallery, so it lives in the same space and you can compare it? And so back then, there was no literature on what is now the problem of backward compatible training, and others have since joined the space. And the idea is very simple. So when you train a new model, don't just train it to minimize the expected error or the average error, which is the standard training loss, but also add a criterion that forces the new model to be compatible, to be comparable with the old gallery. And conceptually, one easy way of doing that is to force the new model to use the old classifier. It's not quite as easy because they could be living in spaces of different dimensions, but that's the key idea. So it's a very simple idea, but it was transformative in the sense that it then allowed companies to consider upgrading to new models without having to go offline for a long period of time and bearing the cost of this backfilling. Okay. So just to give you a sense of what's going on, when you want to be compatible with another model, the first thing that somebody who works in deep learning thinks of is distillation. What is distillation? Well, distillation is you train a model to be close in some sense to another model. And close, for instance, is in the sense of mimicking the input-output behavior. Let's say you have a model, an old model, which is obtained by minimizing some loss function, typically the average error or some proxy of it, for instance, empirical cross entropy, which is computed over, let's say, the old data set. The old data set here is your gallery. Now, backfilling means to do everything from scratch and reprocess relative to some new model with some new loss function, computed over the union of all the data, old and new, right? So we would like something in between, and distillation, for instance, what it does, it trains the new model only on the new data, but then tries to match on the old data, the old model. Here, for instance, using the L2 norm in this high-dimensional vector space, okay? So is this gonna work? Well, certainly there is an easy way of achieving backward compatibility is just to use the old model, right? Never upgrade to the new one. That does the trick. But that, of course, doesn't give you the benefit of improved performance. So how do you improve performance and achieve backward compatibility? Will this do it? And it turns out this doesn't, because when you upgrade, you would like at least to be able to have strictly better performance with the new model compared to the old model when the new data is in the new model gallery, and the new data uses the new embedding, the old data uses the old embedding. And it turns out that if you train for distillation, this is not even guaranteed to do better than the old model, because this is trained on the new data set, the old model is trained on the old data set, and so there's not even guarantee that you will not do worse. So distillation alone would not do it. So what's the idea? By the way, here I use a white background for how discussion, so how actually things are done, and then I use dark background for what discussion, what is being done. So if you don't follow what's in the white slides, don't worry, we'll get back to the dark slide, and then you should be able to catch up. Okay, so as I said, the idea of backward compatible training is to force the new model to use the old classifier. So what does that mean? Typically, when you train a deep network, what you learn is a parametric function that takes the data, processes it through some function. This is called the embedding or the backbone. And then that function passes through another function, and both of these are parameterized. And that function is called either the head or the classifier. So the backbone or the embedding computes some vector space, and then that gets passed through another model that reaches a decision, one of n classes, for instance. So for instance, the old classifier is trained by minimize, again, some loss function, for instance, empirical cross entropy, over the old data set, where you optimize with respect to both the head and the backbone, or both the classifier and the embedding. And what backward compatible training does is it adds a loss term. So you don't want to just enforce the new model to use the old classifier. You want it to give enough freedom to learn its own classifier, but you want some type of loss, which could be cross entropy, could be another one that's design parameters called influence loss, that uses the new model with the old classifier. Okay. And so the characteristics of backward compatible training is that the training loss contains both the unknown new and the known old classifier heads. And this was a paper that was presented at CDPR last year. So if you're interested and curious, you're welcome to take a look at details. Now, this was the first instance of tackling this problem, but the problem is not solved. For instance, if you imagine doing this sequentially, where you update one model after the other over and over and over, what you observe in this example with 3 models is that indeed, the first time you update, you improve over using the old model. from 41 to 56% accuracy. And then when you upgrade to the third model, you improve over the second. But when you try to compare to the first, you notice a regression in performance relative to comparing it from the second to the first. And if you imagine doing this chain over and over and over, eventually you converge to the performance of the old model. So this is an open problem, this is sequential compatibility, and this is something that we and others are working on right now. Now, you may say, well, this is a problem that not very many people have because, if I have a few thousand or maybe tens of thousands of images in my gallery, I can afford to wait a few hours, maybe a few days. Not very many people have billions of data points in their gallery. By the way, what I described is not exclusive to images, could be other types of data. But it turns out that once you realize the problem and you formalize the problem, it shows up everywhere. And so I'll give you another example. So let's say you have a model that runs on the cloud and you want the same model to run on the edge, let's say on your phone, okay? When you design the model for the cloud, you really want the best money can buy. You want the most accurate, biggest, fanciest model. And that typically is optimized for accuracy, not efficiency. And it wouldn't fit on a phone anyway. When you get on the phone, you optimize for efficiency and you can take a hit on accuracy. But now, if you want consistent behavior or compatible behavior between the two, so that if you look at a picture on your phone and you're able to search something, and then you go on the cloud and you don't find it, you get puzzled. So if you want compatibility, then you need to train the model on the edge in such a way that it is not backward in this case because there's no subsequent versions, but you want it to be laterally compatible with the model on the cloud. Okay. And so this is called heterogeneous visual search because you want to build representations that are addressable or that are comparable, whether they are built through a big model on the cloud or a small model on the edge. Okay, so it's exactly the same problem, but there's a twist here because when you train a model on the cloud, typically when you upgrade to the new model, the architecture is fixed. As I said, you'll pick the best architecture you can possibly have. But when you design the model for the edge, the architecture itself is part of the trade space. You can optimize not just over the parameters of the model, but over the architecture of the model itself. And so when we do this heterogeneous visual search, we optimize not just with the parameters of the old model, but with respect to also the old model itself, its architecture, class of functions. Okay. And when you do that, what you observe is that you can obtain accuracy, which is close to, not quite as good as the best model you can run on the cloud, at efficiency, which are as good as or better the lightest model you can run on the edge. Okay. So that's just an example, and there are others. Okay, so that's backward compatible training. Is that it? So are we done now? Are we happy that we're going to just be able to incorporate every improvement we can register, every 1% performance improvement we can now launch and customers will be happy? And unfortunately, it's not quite that easy. And here's another conversation that took part, this time between a product manager after a product had been launched and a scientist. And so the product manager is puzzled and goes to the scientist. Well, you said that the new model was better. And the scientist says, oh, yes, it's much better. It's half the error, twice the speed. Well, then why are customers complaining? The new model is making mistakes that the old model didn't. So then the scientist says, well, of course, when you train a machine learning model, you optimize the average error, okay? And so, of course, there can be specific instances that were right in the first model and wrong in the second. That's just how it is. Well, customers want their old model back. They claim that there is regression. And this term regression means it's a perceived regression. Of course, on average, the new model is better. But when you see errors that were not made before, the perception is, what is wrong with this model? So the scientist is maybe a little bit says, well, let me explain something about how machine learning works. And program manager says, no, let me explain something to you. You are solving the wrong problem. Okay, and that's where the curious scientist kind of steps back and says, well, who says that the right criterion to optimize is the average error? Okay, so that is one dimension that you want to optimize, but in recent years, we've seen that there are many more dimensions where we want to be performant. And this is one, for instance. So iconically, this is how it looks. Let's say you have an old classifier that's represented by this red line, okay? And let's say that this one classifies images between cats and dogs. So the old classifier gets some of them right, cat, dog, cat, and some of them wrong, okay, as you expect, unless the average error is 0. Now you update to the new classifier, which is this dashed line. And the new classifier also gets some samples right and some wrong, okay? So there will be some samples that are right in both the old and the new, some that are wrong in both the old and the new, some that are wrong in the old model and right in the new one. You expect that because the average error has to go to 0. But then this is the problem. There are some data points where the old model is correct and the new model is not, okay? And this is what causes perceived regression. And so we call negative flips those samples, and we call the fraction of these negative flips negative flip rate, or NFR, okay? So then the question of positive congruent training is, how do we minimize or reduce the NFR, the negative flip rate, okay? Now you could say, well, if you reduce the average error, you know, the flips, the negative flips are errors, so eventually you'll squeeze them down to nothing, okay? So this should come automatically by optimizing the standard losses that minimize error, and this is actually not true. So unless you can reduce the average error to 0, you always observe negative flips. And so the two criteria, optimizing the error rate and the NFR, are typically independent. So I'll try to illustrate that with a cartoon and then with some data, okay? So imagine that you have a learning task. What is a learning task? A learning task is a data set, okay? So if you think about that for a second, when you train a machine learning model, in particular a deep learning model, the only thing it knows about the task is the data set you gave, training set, okay? So that specifies the learning task. After you've done training, whatever information about the task was in the data set is now in the weights of the trained network, because there's nothing else left. So if you train a model once, you get one set of weights. And imagine that these weights are some point in some huge dimensional space, you know, tens of millions, hundreds of millions, now trillions, okay? If you now take the same exact data set and train same exact model, minimizing the same exact loss function, just with a different initial random seed, you get a different set of weights, okay? And if you do it multiple times, you obtain different sets of weights. Now, these are all different set of weights, but they're all equivalent in the sense that they all implement models that achieve the same average error rate, okay? So for instance, if your model is RSNet 152 and it's trained on ImageNet, those will have an error rate of 21.7%, all of them, okay? You can try this 100 times, you'll get 100 different models, all of them have average error rate of 21.7%. But they're all different, not only in their weights, they're also different in what errors they make. So out of the 21.7% of the samples that are incorrectly classified, they differ among each other on 10% of the sample, so roughly half, which is surprising and puzzling, okay? So what it means is that all of these errors in the space of models, all of these models in the space of models, if you imagine the origin of that space being the ideal model that doesn't exist, that always gets everything right, right? All of these models sit on some gigantic hypersphere. And the way they move along the sphere is by trading error, okay? I'll make one correct and I'll give you one wrong, okay? So you can move on this iso-error sphere by trading errors, basically. But you cannot push beyond 1.7%, 21.7%. Okay, now keep this in mind, and now let's say that you have a new model, and the new model is somewhere on a smaller sphere because it's more powerful, trained with more data, achieves smaller error, okay? Great. Now you want this model, okay, to be compatible, to be close in some sense to the old model. And so again, distillation comes to mind. What does distillation do? poses a penalty that tries to force the new model to be close to the old one. Okay, but by doing that, you trade off average error because you're getting away from the origin. So which means that the goal of getting close to the old model and keeping the error rate down are in conflict with each other in distillation, but not in positive congruent training. In positive congruent training, you want to move on the iso-error sphere, which allows you to get close to the old model without losing anything in error rate. And the way you do it is by mimicking the old model, not everywhere, but only when it's right. Okay, and that's the basic idea of positive congruent training. Okay, so just to give you some numbers, some examples. Suppose that the old model is one of these architectures, let's say AlexNet, SqueezeNet, all the way to ResNet-152. These are increasingly powerful architecture that achieve increasingly high accuracy or increasingly low average error. And let's say that your new model is one of these. Okay, so obviously, if your old model is a mobile net and the new model is no mobile net, you get different models. They may be different, but they all have the same average accuracy. Okay, so the change in error rate is 0. Okay, and of course, if your old model is in AlexNet and the new model is ResNet-152, you get a 22 points improvement in average precision. Okay, but when you look at the negative flip rate, even the ones along the diagonal, where the old model and the new model are the same, is not only is not 0, but even as your architecture becomes more and more powerful, it's stubbornly around 5, 6, 7%. Okay, it just doesn't go down to 0. And even for changes from old new that achieve performance improvement of 22 percentage points, you still cannot get the NFR down below 2%. Okay, so positive congruent training aims to not only minimize the average error rate, but also minimize the NFR. This is a new problem. There was no literature on this problem. And the first paper is going to appear at CDPR 2021 in a month or so. Okay, how does PC training work? Typically distillation works by training the model so that let's say the embedding or representation, in this case are cologits, or the normalized layer to be as close as possible to each other, measured by KL divergence or R2. In positive congruent training, we don't do that. We still use focal distillation, which is a form of distillation where the bias towards putting these two models close to each other is weighted by the ground truth value of the labels. So it's higher when the old model gets it right, and it's lower when it gets it wrong. So here's the distillation loss. This is the cross entropy loss, which is a proxy for average error. If the sample is correctly classified by your classifier, then you impose a higher penalty on the distillation loss. And if it is not, then you impose a lower penalty. Okay. You may say, why not alpha is equal to 0? Well, there's many details for how to make this work, and we'll not get it. Okay. So when we came out with this paper, we thought, okay, what are we going to compare it with? Because there's no benchmarks here. So we thought, well, when you average models, we know that the error rate goes down a little bit, because if you have in mind the picture of the iso-error sphere again, when you do a chordal average, the chordal average is closer to the center than any point on the surface. And so you do see a little bit of a decrease. And so we thought we're just going to do ensembles of multiple models, both old and new. This is, of course, not a viable solution. You cannot run ensembles at inference time because that multiplies the cost of inference by an integer, which is not acceptable. But what we noticed back then is that while the error rate goes down a little bit and then sort of stabilizes, the NFR, as you ensemble more and more model, keeps going down. So this is another puzzling phenomenon that we don't quite know how to explain. And in fact, it goes down so much that ensembling is currently the paragon performance. So it's not just a baseline, it's actually the best performing method, even though while averaging the model, the new and the old average don't know about each other. So in a sense, we call this future proofing, because by ensembling the old model, okay, indirectly, you're going to minimize the NFR for future models once you try to do PC training of those. Okay. There are some numbers that shows you that when you don't apply PC training, the NFR is in the order of 6-7%, depending on data sets and modalities and so on and so forth. And with focal distillation, you get it down to around 2%, and with ensemble, it goes down even more. Okay, of course, ensemble is not viable, and so here again, there are open problems or how to do this in a way which is not only guaranteed to minimize negative flip rate, but also efficient computation. So one question that we ask ourselves is, well, these negative flips, what do they look like? Are they points that are just very close to the boundary or very uncertain? And so then it's just a matter of stability or perturbations or robustness. And the short answer is no. These points are everywhere. And so what you can do is you can draw, as a function of the empirical uncertainty, you can draw a line at 95%, say, I'm going to throw away anything which has a confidence below 95%. What do I have left? Well, you still have about a 1% NFR. And in the process, you threw away 68% of the data, which is the histogram in blue. And the orange is the histogram of negative flips. Okay. So the short answer is not points that are close to the boundary or that have high uncertainty. Okay. So I started this talk by talking about Graceful AI. I haven't said what that means. So these are just two examples of problems where we want to train deep learning models that not only tries to optimize performance as measured by error rate, but also that accounts for compatibility and transition from one model to another, either over time, as in backward compatibility, or over space or embodiment as positive congruent training. Okay. So, and typically, these deep learning models don't, even though they're trained end-to-end, and we like to think of that they do everything, but in reality, they're often inserted into very complex engineering workflows. There's stuff that gets done with the output. And if you have negative flips, that could break post-processing pipelines. And then all of a sudden, the whole system has to be re-engineered, which is extremely disruptive and costly. So we want to update our models in such a way that it will not disrupt any of the post-processing or pre-processing pipelines. Okay. And so I thought that Graceful AI, especially for something that was kind of put down in writing around the beginning of the year, was a proper name for it. As I said, now that we know that this problem can be formalized and addressed, we find it everywhere. And so there's going to be a tutorial at the next ICCD on more general cross-model compatibility. Some of our partners also from Microsoft will participate in that. And this is something that we also apply on language models. For instance, Lex is a natural language service that creates conversational bots. And a conversational bots uses deep learning models, but these are inserted in very complex workflows. And so changing the model and updating it, even the average error rate improves, can be very disruptive. And so we have a paper coming up at the next ACL on implementing positive congruent training for language models. Okay, so I'm 30 minutes in, and this is kind of hopefully something that gives you a sense of what it means to do customer-obsessed research. In academia, we spend most of our creativity goes into inventing problems or creating problems that don't exist, and then hoping that they will be relevant somehow. And one of the luxuries of being at AWS is that we're constantly bombarded by problems that are very difficult, very interesting. And then we look backwards and try to think, okay, what are the common and generalizable parts of this? And everything I've said so far, if you've noticed, pertains to relations among learning tasks. As we said, a learning task is a data set. After the model is trained, that information is in the parameters. Okay, and what we have talked about is relations among models, okay, and therefore relation among learning tasks. And so this is a very important topic in machine learning. So even generalization is the simplest instance of this problem, where you have two data sets, therefore two learning tasks, okay, which you assume are coming from the same distribution. One is a training set, one is a test set, okay? And so you try to figure out ways for the two tasks to be close to each other. Now, in transfer learning, you know that the two are from two different distributions, and so there is some distribution shift or covariance shift, and you try to figure out how to get one model closer to the other. But in order to talk about the relationship among learning tasks, you have to understand in what space do learning tasks live. Is this a space that has some type of structure, some type of topology, so you can tell whether two tasks are close to each other? And what is this topology, right? So clearly, the data set itself is not a good representation of a task, because I could give you a completely different data set with different number of images, different size of images that represent the same learning task, which is of figuring out whether there are cats or dogs in the image. So clearly, the raw data is not a good representation. The weights are also not a good representation, because we've seen that there are lots of different weights, in fact, infinitely many, that implement the same input-output behavior. So really, what we are after is to represent a learning task, neither the data set nor the weights, but the information that they both share, that they contain, okay? What is information? So when we talk about a trained model in a neural network, it's a deterministic input-output map. So when you try to evaluate information as we've learned it from communication theory, you get nonsensical results. And so this is actually a controversial open issue, how to define and compute information in training models. And then there are subtleties that come when you train the learning model, where it's obvious that there are very important phenomena that happen in the transient dynamics of learning that affect the long-term behavior of the model. And so there are notions that we introduce of task reachability and information plasticity that I'd like to at least hint at in the next 10 minutes. Okay. Okay, so as I said, a learning task is a data set. There's nothing else known before you start training. And after you're done training, whatever information about the task was in the data set is now in the weights of the trained neural network. Okay? Now, if all a neural network can do is to memorize the data set into the weights, then it's not very useful, because you will never see the data set again. So how do you measure how useful, how well a model has learned the task? Well, you take a test set, okay, data you've never seen before, or even future data that you will see at some point, and then you pass it in, you will get some type of activation, some type of function, right? And then this function will be passed through a classifier, you will get a loss, and you evaluate this loss to see how well your model is, right? And typically, how different these two are, so how different the training loss, which you know and optimize, is from the test loss, which you cannot compute because it pertains to future data that you haven't yet seen. How close these two are is a measure of how well the model generalizes. And so there is an industry of generalization bounds. Here are two. The one below is the one non-pack-based bound. And what I want to point to you is that both of them say that the test error, which is what you don't know, but you would like to make small, is less than the training error, which you do control completely, plus some term that has some constants, and this thing that I've written as the mutual information between the weights and the data set. Okay, what does that mean? So here I've used notation from Shannon mutual information, which is, but intuitively, it's the information that the weights contain about the data set. Okay, now I have to tell you what that is, because formally you can write it and you can write a bound, but when you go and try to compute it, this is nonsense. Okay, so what is information in the weights of the data set? So the notion of information comes from communication theory, and I once was at a conference with a group of friends, and Robert Stefano came along, and he told an anecdote of when he was a student, and Norbert Wiener stormed into the office and said, you know, information is entropy, and that left himself and all the students puzzled and said, what is that? What did he say? And that kind of forced them to think very deeply about what that meant, and that basically was the birth of information theory. The problem is that entropy, information, these are properties of distributions of random variables, okay? In the learning setup that we are under, we have one data set, not a random variable, and once we're done learning, we have one set of weights, not a distribution. So there is no entropy, okay? We have one data set, okay, zero entropy, and one set of trained weights, okay? So the data set has zero entropy, so the uncertainty on the task is zero, and so the uncertainty of the weight given the data set is also zero. So it's nonsense. But then, of course, you could say, well, yes, you have one data set, but if you were given a different data set for the same task, it's really, you really have a distribution of data set. You just happen to only see one of them. Okay, so if you do that, then what happens is that the training process, other than the random seed, okay, is actually deterministic, even if you use stochastic gradient descent. So you converge to a single set of weights, and that single set of weights is the deterministic function of the data set, and therefore has infinite differential mutual information. Okay, so no matter how you look at it, this term is either 0 or infinity. If it's 0, then the path-based bound is not defined because there's no hypothesis space. If it's infinite, it tells you that the test error is less than the training error plus infinity, which is not very useful. Okay, so really the notion of what is information in the deep network is non-trivial and needs so we've been working on this for several years, and we have a definition, but we are told from information theorists that unless Shannon said it, it's not information theory. So we had to find where Shannon had said it, and in fact he had said it back in the 50s. When Shannon tried to compute and measure the entropy of written English, what he did is the following: took a sentence, and then he started perturbing the sentence, adding noise to the sentence, changing characters, okay, and measuring the effect it had on the reconstruction of the sentence. If you have a sentence and you start changing characters, and you can still tell what the true sentence was, that there was not a lot of information in this character, right? But if you change one single character and all of a sudden you get the wrong meaning, or you reconstruct the wrong sentence, then obviously that was a very informative character, right? So in the case of Shannon, you had the data, you added noise to the data, and then you reconstructed the data. So it's all about the data. There's no semantics there. In our case, it's different because we don't have to reconstruct the data. We have to use the data to say something about the task. And so in this case, it turns out that this notion is not meaningful, but we also need to account for the desired performance in the task. Okay, let me give you an example. Suppose your task is to discriminate between airplanes and cartoon characters. Okay, how much information do you need, okay, to store in the weights of your deep network for you to learn this task? Well, it depends. If you're okay with 50-50 performance, you don't need to store anything. You flip a coin, you're right 50% of the time, that's good enough for you, that's fine, zero information. If you say, no, I want 75%, okay, then you might get away with storing just enough information to compute the color histogram. If it's mostly blue, you say airplanes. If otherwise, you say cartoon characters. Okay, and now if you apply perturbation just like Shannon did with the characters, you don't pay a price in terms of performance. And now you can, instead of applying the perturbation to the data, you apply the perturbations to the model, which are dual in the first layer still. Okay, but if all of a sudden now you want 99%, now you have to be able to discriminate airplanes that look like cartoon characters or they don't have a lot of blue. And as soon as you start moving that, you pay a big price. And so there's a lot of information that you need to store if you want high performance. So how it is defined technically? You take a network and you train it however you want, deterministic, stochastic, whatever architecture, it doesn't matter, you get a set of weights, okay? Now you pick whatever distribution you want. Okay, I'm gonna use a Gaussian just for convenience. You can take whatever you want. This is a variation optimization problem, it's infinite dimensional, okay? And then you start applying, hypothetically, in practice you don't do that. Hypothetically, you start perturbing the weights by adding noise according to this distribution until the training loss, not the test, the training loss which you measure, okay, reaches a threshold, okay? So you add noise as much as you can in all possible directions. In some, you can add a lot of noise, in some, a little less, until you hit a threshold. And that amount of noise you add is the redundant information, and the difference from the information in the, you need to store the data set is the accessible information, is the information that the model has learned that it can use for classification. Okay, so to define information, you need to solve a constraint optimization problem. The good news is that the first order approximation of this gives you the log determinant of the Fisher information matrix, which is a well-known concept. So it's good that at least in some simple case, introduce it to something known. But more in general, if you write the constraint optimization in Lagrangian form, you get an expression which we call the information Lagrangian, and this can be optimized with stochastic gradient descent. Okay, and this is actually the same stochastic gradient descent you use for training the deep network. So, and lo and behold, that information Lagrangian is actually what goes inside the path-based path, okay? And so this is actually quite beautiful because the definition of information has implicit a variational principle, which is information Lagrangian, minimizing which guarantees maximum generalization. And so here you can see that generalization is not at all about dimensionality, it's not at all about reducing the dimension. In fact, the bigger the dimension, the better, but what you want to reduce is the information that the weights contain. And this is one of the lessons of deep learning, is that it pays off to go up in dimension, but to go down in information. And there are many mechanisms that deep network use to reduce information, including dropout, including pooling, and so on. Okay. All right. So what is new? So we have a definition of information, which actually is well defined, even for the deterministic model trained on a single data set. Okay. We have an inductive principle, and this is actually computable for real-world networks and gives non-vacuous generalization value. I want to give you a vignette of some of the really puzzling phenomena that are happening. So now that we know how to measure information, we can measure it while the network is training. And so you can imagine that as the network is learning, as the number of training epochs progress, you would expect the amount of information stored in the weights to go up, and maybe at some point with diminishing return, approaching an asymptote. But that's not what happens. What happens is the blue curve, where information first go up very steeply and then goes down. So you first memorize a lot of information, and then you forget a lot of information until you settle to a very low information level. And this forgetting is happening while performance in the task, which is accuracy, which is the green line here, is improving. So even as you're forgetting, you are learning, which I really like as a person of a certain age, because when I forget things, I think that I'm still learning. So, and this phenomenon, by the way, is not specific to deep networks. In fact, this is a very well-known phenomenon in biology. It's known as critical learning period. So if you mess with the transient dynamics during this initial phase, then you never achieve good performance in the task, no matter how long you train. Okay. And now, when I said that this information Lagrangian is what is minimizing deep networks, if you are a practitioner of deep network, you say, well, not really, because we only minimize the training loss. We don't minimize this information term. But in fact, you do. And so what you notice is that, especially if you think of the Fisher information, which is the second order approximation, high Fisher means high curvature of the loss landscape as you are converging, which means that during the transient, you're going through very narrow bottleneck regions with very, very high curvature. And then the landscape opens up into wide valleys where curvature is very low, information is very low. And so this is happening. As you're training with stochastic gradient descent, and so this curvature adds a drag term, which actually minimizes its information. And so this is where the inductive bias of actually comes from. All right, going back to the initial focus on Graceful AI, what does all of this have anything to do with the relation between learning tasks? Well, now we can define a topology in the space of learning tasks. Now that we know how to compute information in a trained network, we can compute the information needed to learn two tasks jointly, minus the information needed to compute one of them. And this is an asymmetric distance that correlates highly with the ease of transferring information or going from one task to another. After you train a task and you want to learn another task, you want to move along the space of learning task to the new one, for instance, using fine-tuning. But you would like to predict how well you would do, how long it would take, and how much it would cost to get there without actually doing the experiment. Okay, and to do that, you can compute this distance. Okay, and this is actually done at scale, where you can have a large number of models, for instance, in a model zoo. And given a new task, you would like to know which model should I try to fine-tune from so that I can get the best performance. But you don't want to try them all and see which one gives the best performance. You would like to predict beforehand. And so what you can do is you compute this distance, which is called the task to back distance, and then only pick the closest point and fine-tune from that. So what you can see here is the red cross is the performance achieved by picking the closest point, as opposed to the picking the closest task, which may not be the most powerful model, by the way, compared to the triangle, which is pre-training from the largest available model that was trained on all the possible available data. Okay. There are a lot of subtleties into how this dynamics happen, but in the interest of time, I will skip. I just want to remind you of some of the concepts that have been introduced in the process of unraveling this. So we have a definition of information that is computable for deep networks. When we fine-tune from one task to another, if that happens during the transient, it's reversible. If it happens after we cross the critical periods, it's irreversible. So there is a notion of information plasticity during learning that is not just biological. Okay, it's not that you're getting old or you cannot teach old dogs new tricks because of aging. It's really fundamental information phenomenon at play. And now we can predict whether we'll be successful transferring information from one task to another without actually doing an experiment or trying. We can predict how long it will take. We can predict training time. And there are tasks that are nearby, yet they're not reachable from one another because of this narrow bottleneck. And there is a notion of task reachability that I can talk to offline if interested. Okay, and all of these concepts are not toy concepts. They are implemented in real world networks at scale. So I've given you some examples, mostly restricted to classification. Ideally, we want to go beyond, model train and then an update to a model. We want to go towards continual and lifelong learning. This is a long path. We have techniques for dealing with these irreversible dynamics. There is a paper also coming out at next DPR called linear quality fine-tuning. There are a lot of interesting open issues that relate to forgetting, security, privacy, fairness, and so on and so forth. And I'll be happy to talk to anybody offline. I'll leave a list of references on the slides for later peruse. And if you're curious, anything interesting we do ends up on Amazon Science. I invite you to peruse that website and reach out to me if you have any questions. Thank you.
That's a fantastic talk.